Hello! Today I'll be talking about the characterization of particulates in Australian coal mines. Though I'm originally from the US, I've been in Australia for almost a decade now. So I was here when the first case of CWP was identified in 2015, after almost 30 years without a reported case here in Queensland. For a time, Australia thought they had eradicated the disease, but upon further investigation, it was found that it just wasn't being detected properly. Since then, the health surveillance and exposure monitoring systems have been overhauled. I was working for ISMDAR at the time, which performs health and safety research in mining for the Queensland government, similar to NIOSH in the US, but on the state level. That led me into the dust research, and since then, I've moved to the University of Queensland to further pursue the dust characterization research. I'll start with a bit of background on Australia and the mining environment before I get into the characterization data. Australia is 80% the size of China and about the same size as the US. Most of the coal is concentrated along the east coast in the states of Queensland, which covers the northern half of the east coast, and New South Wales, which is situated below that. Each of the 6 states and 2 territories in Australia have their own state-based mining legislation and systems. In Queensland, there are 40 open-cut coal mines and 8 underground coal mines producing 240 million tons per annum. This translates to roughly 8,000 underground coal mine workers in Queensland, working in only a handful of seams. In New South Wales, there are 41 coal mining operations. This includes 20 underground mining operations, 16 of which are longwalls, and 21 open-cut coal mines. In Australia, most of the coal mines are owned by large multinational corporations. There are no small mines that employ only a handful of people in coal, like there are in the quarrying and opal sectors. Australian coal seams tend to be very tall, with seam thicknesses up to 8 meters or 26 feet. 6 of the 8 mines in Queensland are longwall mines, and the other 2 are rim and pillar. There are top coal caving longwalls used, and some of the high-reach longwalls mine up to 15 feet or 4.5 meters. Most of what is produced is metallurgical coal, and Queensland has 35 billion tons of high-quality coal reserves. Continuous miner development is done predominantly with miner bolters, as opposed to cut and flit, with separate mining and bolting units. The industry is very safe, with only a small number of fatalities annually. Both Queensland and New South Wales have compulsory health surveillance schemes, which means every coal mine worker is periodically checked, including a chest x-ray. In New South Wales, it's every 3 years for underground coal miners and 6 years for everyone else. In Queensland, it's every 5 years for all workers. Queensland has recently implemented the health surveillance scheme for metal mines and quarry workers as well. Having a compulsory health surveillance scheme means there is a much better chance of catching cases as they progress. There's also a robust universal healthcare system and workers' compensation scheme. In Australia, exposure monitoring is on the individual person and not the designated operator. This is in contrast to measuring continuously over a shift for that role that does not allow for breaks or job rotation. As such, the dust exposure would be expected to be higher for a designated operator than for an individual being monitored. Prior to the re-identification of CWP in Queensland, the exposure limit was 3 milligrams per cubic meter with shift adjustment. Queensland mines normally work 12-hour shifts, 7 days on and 7 days off. In Queensland, the sampling is performed by fee-for-service hygiene consultants and is then reported to the inspectorate by the mines. Different consultants use different brands of sampling equipment. Sampling is measured from portal to portal, meaning hygienists don't always go underground to observe conditions and may rely on the worker being sampled to fill out a report on their activities for the day. In New South Wales, the exposure standard of 2.5 milligrams per cubic meter was adopted in 2004 when the flow rate changed to 2.2 liters per minute. No shift adjustment is applied. Compliance sampling is performed by Coal Services, the statutory body, so all the sampling is done using the same fleet of equipment and a consistent approach. Most of the Coal Services personnel are ex-deputies with mining experience. During the sampling, Coal Services inspectors go underground to observe the work and talk to the miners about their dust control and operator positioning. Samples are taken from crib room to crib room, the Australian term for dinner hole, which means samples are of shorter duration and don't count the travel time to and from the section. Coal Services uses the Casella-Higgins dual-type cyclone elutriators. Queensland uses both the Casellas and SKCs. Both Queensland and New South Wales now have 1.5 milligram per cubic meter standards for respirable dust. Queensland adopted theirs on 1 September 2020. At the same time, it lowered the respirable crystalline silica exposure standard from 0.1 to 0.05 milligrams per cubic meter. New South Wales dropped the respirable crystalline silica exposure standards from 0.1 to 0.05 on 1st of July 2020. It then dropped the respirable dust limit from 2.5 to 1.5 milligrams per cubic meter on the 1st of February 2021. At the same time, it set a diesel emissions limit by elemental carbon of 0.1 milligrams per cubic meter. Queensland's diesel emissions levels is a recommended guideline, not a statutory limit. The limit for respirable dust in mineral mines and quarries is 5 milligrams per cubic meter for both states. This figure illustrates the mine dust lung diseases reported to Resources Safety and Health Queensland as of 30 September 2021. The teal color represents the cases of coal workers' pneumoconiosis, while the black represents cases of silicosis. As you can see, the majority of cases are not CWP. In fact, only about a third are CWP, and a growing number are silicosis and COPD. From 1984 to present, there have been 233 cases of mine dust lung diseases reported in Queensland. 95 of these are non-pneumoconiosis cases. 54 cases of CWP have been reported, along with 55 cases of silicosis and 29 cases of mixed dust pneumoconiosis. There have also been a number of cases of silicosis reported by engineered stone benchtop workers. These can be very aggressive and affect younger workers after only a few years due to the high silica content in engineered stone. Dry cutting has been banned in New South Wales, Queensland, and Victoria, and a new National Code of Practice was published in 2019. In September 2021, Resources Safety and Health Queensland, the regulator for the Queensland mining industry, published the baseline review of the Occupational Safety and Health Report. This report was a joint undertaking between Ernst & Young and the Minerals Industry Safety and Health Center staff here at the University of Queensland. It includes a wide range of health risks that affect workers across the 4 inspectorates within RSHQ, which are coal, mineral mines and quarries, petroleum and gas, and explosives. This report includes analysis of the dust, silica, and diesel exposure data that is available for the coal and mineral mines and quarries sectors. This document is available at the website listed on the slide if you're interested in having a look at exposure data or a review of any of the other hazards. This graph shows a comparison of the chemical composition of the respirable dust in continuous miner sections in the US versus Australia. The US data came from Emily Sarver et al.'s 2019 paper. I collected the Australian samples and sent them to Virginia Tech to perform the analysis. This figure shows the percentage of various mineralogies by count of the particles. The light blue is the carbonaceous material, which includes the carbon particles, which is both the coal dust and the diesel particulates. The automated routine used here can't distinguish between the two, but I'll talk more about the diesel later. There's a large portion of aluminosilicates in orange and some silica represented in red. The carbonates are mostly stone dust, and there are occasionally heavy metals or other particulates present. Except for Mine 3, who was cutting a section with stone in the working section, the Australian mine samples in this set seem to have relatively more carbon in the samples than the US mines. This may be because Australian mines are thicker seams and typically leaving coal roof and coal floor. The Mine 1 through 4 data is published in a paper in the Minerals Journal, and a link for that paper will be on the final slide. Not all mine dust has a uniform particle size distribution. It can vary quite considerably from one mine to the next. This figure shows the count of particles in 3 size classifications for continuous miner sections in 4 different underground coal mines in Australia. As you can see, the particle size distribution varies from mine to mine, even for the same type of mining process. The particles less than 2 microns in size account for between 55 and 80% of the size distribution, while the particles over 4 microns only account for less than 14% of the samples. But when the particles larger than 10 microns appear on the filter, they do contribute a much more significant portion of the mass. For instance, in Mine 3, particles over 10 microns account for 0.5% of the count of particles, but 18% of the mass on filter. During this time, it was also identified that one of the brands of cyclonolutrators was oversampling by up to 30%, which was leading to some of these oversized particles. This necessitated a change in flow rate for those samplers going forward and invalidated much of the historical data collected with those samplers. Mines with a greater number of large particles may have a harder time complying with statutory limits, but may not necessarily pose more of a health hazard. The size of these particles can greatly affect the health hazard. I'm now analyzing the characterization of dust from the Australian mines at the UQ Julius Kruschnitt Mineral Research Center, abbreviated JKMRC, on the Mineral Liberation Analyser, or MLA for short. The MLA is normally used to identify minerals in polished sections of drill core or lump materials, and analyzing for particulates on filter is a new technique. Michelle Elms in the Geology Department has recently completed her PhD on the development of a method for particulates on filter using the MLA for inhalable samples for environmental dust. With the MLA, I've been able to identify 26 different mineral types as opposed to the 7 broader categories of minerals in the US analysis. The MLA can detect particles down to 0.52 microns in equivalent circle diameter. Historically, the characterization of dust that was performed in the 1980s was only able to look at select components of the dust and the overall size distribution. With this technique, I can look at the individual particles for their size, shape, and the range of mineralogical composition. This allows me to determine a size distribution for a particular mineral component, such as quartz. These samples were analyzed on the MLA. They were collected from 3 mines that are different mines and seams than the US comparison shown a few slides ago. This data set consists of 28 samples collected from 12 locations over the 3 mine sites. Some of these were taken in quadruplicate for repeatability purposes. The mineralogy has been analyzed on 17 of the 28 samples, and reliable particle size distribution is available for 11 of these samples, as some were too overloaded to get a reliable particle size information. Each filter has between 150,000 and 800,000 particles analyzed on the MLA, for a total of 8.25 million particles analyzed on these filters. Similar to the US data, the major trends hold the same, with relatively more carbon in the samples and just a small amount of quartz. What's interesting is that 2 of these mines there have high amounts of calcite on the longwall midface samples, but not nearly those quantities of calcite at the main gate. I talked to one of these mines and they have a calcite lens in the coal cleat that's causing the high calcite levels. So they expected to see calcite in the samples, but were very surprised with just how high the concentrations are. Tests 6 and 7 were the same longwall midface on different days and show quite a different makeup. Mine 8 has extremely consistent mineralogy throughout the mine, and there's very good agreement between the paired samples showing just slight variability in composition. It's important to understand the dust being generated underground, as there are several sources that may be contributing to this dust. These include not only the cutting of the coal, but the diesel vehicles on the section, stone dusting, and other secondary activities being performed, such as shoveling. It shows the silica content of the dust, as well as many of the alumina silicates or clay minerals that are present. These alumina silicates are also of concern, as particles of these have been found in lung tissue along with the silica. This figure shows the overall particle size distributions of the dust in mine 6 and 8. Mine 6 follows the trends previously observed in the particle size distributions of mines 1 through 4. The dashed red lines represent the continuous minor sample, which is coarser than the other particle size distributions. Lines that are lower and to the right indicate a coarser distributions, while lines that are higher and to the left represent a fine particle size distribution. The darker red line represents the mid-face samples, which is finer than the other particle size distributions, and the main gate sample is between those. The secondary recovery shows a similar particle size distribution to the main gate samples. Mine 8, that showed the consistent mineralogy, also, unsurprisingly, shows very similar overall particle size distributions. Carbon is a significant portion of the mineralogy, so the overall particle size distribution is heavily weighted towards the carbon particle size distribution. With the data on the individual particles and their compositions, a particle size distribution can be determined for each individual mineralogy. Many particles are made up of multiple mineralogies, so this data is filtered to reflect only particles with greater than 50% by weight of a certain mineralogy. The kaolinite, shown in green, tends to be on the coarser side of the distribution in most of the samples. The muscovite in orange can vary from a coarser to a finer distribution. And these are both types of alumina silicates. The shape of the distribution of the quartz in the sample can vary from the normal shape of the curves for the rest of the mineralogy. This can be seen in sample 40, where the quartz starts out in the middle of the distributions and rises swiftly to become one of the finest distributions. What is interesting to note about the differences in these distributions is that in mine 6, the one that has the much greater variation in the overall particle size distributions between locations in the mine, the particle size distributions for the various mineralogies are much more homogeneous. While for mine 8, with the very narrow banding of the particle size distributions, it has a much wider spread of particle size distributions for the individual mineralogies. This figure shows the mineralogies broken out for various size fractions. These size fractions are less than 1 micron, 1 to 2.5 microns, 2.5 to 4 microns, and 4 to 10 microns. The overall mineralogy is shown to the right of each graph. Here I've cut the graphs off at 40% and 60% respectively to allow for more detail to be seen at the top half of the graphs. The carbon is shown at the bottom of the graphs, and everything from 0 to the percentage indicated on the graphs is carbon. In these samples, there is the most carbon by weight percentage in the smallest size fraction of less than 1 micron. In sample 6MgO3, the carbon continues to decrease in the 1 to 2.5 and the 2.5 to 4 micron size, and then rises again in the 4 to 10 micron size range. There is also a rise in the percentage of muscovite in the largest size fraction. In sample 8SC40, the carbon percentage continues to decrease as the particle size increases. The percentage of calcite is greatest in the 1 to 2.5 and 2.5 to 4 micron size in both of these samples. The calcium silicate percentage also seems to increase slightly in the larger size fractions. The MLA uses the data view software, which gives an image of the individual particles, which is color-coded by their mineralogy. Here's an example of what some of those particles look like. While some particles are a single mineralogy, there were more particles of multiple mineralogies than I expected to see, especially in the larger size fraction. The MLA can detect particles down to the 0.52 microns in size. The pore size in the respirable filters I'm using is 0.45 microns, so there would not be reliable data below that size to begin with. There are a variety of shapes to the particles as well. Some are ovaloid, but there are also many particles that are long and narrow and have a high aspect ratio. Several examples of this can be seen on this slide, as the smallest sizes of the particles tend to be more round to oval shaped and more of a single mineralogy, but that may be affected by the limits of detection. Individual particles on the filter are assigned a number that can be interrogated in a number of ways. These include the spreadsheets of parameters that are generated for the particles, as well as a visualization of the particles. The spreadsheet data includes the area, perimeter, max span, length, breadth, and a calculation of density based on the various mineralogies, which provide a weight percentage. Here are some examples of the particles with multiple mineralogies, showing the shape of the particle and the location of those mineralogies within the particle. The numbers beside the mineralogies are the areas for each of those mineralogies in the particle shown. The MLA data software allows the particles to be sorted a number of different ways. One of the parameters I can sort by is the maximum particle span, which shows a number of fibers or elongate mineral particles on the filter. These needle-like fibers show a variety of mineralogies. This particular sample includes kaolinite, carbon, calcite, calcium silicate, and even an unknown particle. Similar to the Virginia Tech methodology, the automated routine in this methodology, looking at the carbon particles, cannot distinguish between the coal and DPM. However, the DPM particles have a unique shape, and they can be picked out of the SEM field manually on an optical image. In the photo at the bottom right, you can see the chains of agglomerated diesel all over the filter. The black dots you see are the pore spaces in the filter, which are the 0.45 microns. To some extent, certain particles can be differentiated visually in the MLA data by the shape of the particle, but this is not reliably done manually, and a large number of particles are questionable as to whether they would be coal or diesel. When diesel particulates are generated, they are normally in the nanometer range. Agglomeration involves the growth of particle chains and clusters through the collision of the particles. We don't know if this agglomeration took place on the filter or if it was picked up like this through agglomeration in the mine. But this is more diesel than I expected to find and is a subject for further investigation in my studies. I also found some particles with an iron, chromium, nickel content, which the MLA has identified as most closely resembling stainless steel. Now, this wasn't something I was expecting to find in the samples either. The fraction of stainless steel varied from 0.02 to 1.1% of these samples. In talking to the mines, no stainless steel equipment being used in the mines could be identified as the source, and it's been theorized that these particles may be coming from the diesel engines themselves, which are being operated in the mines. Further investigation is needed into the potential sources of this material, because there's not a direct correlation between the amount of carbon and the amount of stainless steel in the samples. I hope this presentation has given you an appreciation for the types of information that can be gained from dust characterization. The results paper on mines 6 through 8 is in final draft and should be submitted for publication very soon, which will provide more detail on the information gained from this analysis. A comparative analysis of the Virginia Tech and MLA methodologies is also underway. Several samples have already been analyzed using both methodologies, and there's another set of samples in the lab awaiting analysis to complete this comparison. There are a few differences in methodology that will necessitate filtering to a subset of the data for comparison. One such difference is the bottom size of the particles capable of being analyzed, which is 0.9 and 0.52 microns respectively. I expect these results to be published in 2022. Sampling campaigns have been undertaken at 4 metals mines, including their smelters and processing plants in Australia so far, and this data is proving even more interesting than the coal data. So far we've found 40 different mineralogies present in the metal samples as opposed to the 26 in the coal mines. For all of these mines, we have collected inhalable samples as well, which provides us with an overall dust level to compare to the respirable dust level. We've been trialing several different sampling methodologies with IOM samplers and 3-piece cassettes to work out what is the most suitable inhalable technique for our characterization purposes. The initial respirable dust samples were collected from mines 6 to 8, were analyzed from 6 frames across the entire filter. Initial looks at the spread across the filter shows relatively good consistency, so we've moved to just analyzing a punch from the edge of the filter for the later samples. I want to do a more in-depth analysis on the spread across the filters as well. Australia is using SKC and Casella-Higgins dual-type plastic cyclones, which are different than the Dorr-Oliver cyclones used in the US. Further sampling is planned next year for underground metals mines and underground coal mines, which will expand the data set we are building on the dust being generated in Australian underground mines. We are also talking to other parts of the industry like quarries, surface mines, and engineered stone benchtop cutting operations about potential opportunities for characterization of their work. This would help expand the dust database that we are creating and provide valuable information on the dust characteristics faced by other industries. There is also potential to use the knowledge gained to inform dust control methodologies. For instance, the longwalls with the significant percentages of calcite, if they use chemical surfactants, it would be much more impactful to target the calcite than it would be the coal. I hope this data can be used to inform health-related dust work as well. Most lung tissue studies that are currently being undertaken involve crushing samples of coal in the lab, but as you can see from the data presented today, not all coal dust is coal, and there can be several sources of dust within the mines, and the particle size distribution of the dust may change based on the location in the mine and the equipment generating the dust. This concludes my presentation, and I want to thank you very much for listening. I hope this talk was able to provide you an overview of the operating environment and the challenges we face in Australia, and the characterization work that has been done to date. I do believe that this work is important for our understanding of dust exposure and control. I'm hoping to use what we learn about the characterization of dust, including the particle size, shape, and chemical components, to help the mines better control their dust at the source. A further research goal of mine is to try and relate the characterization to the potential health impacts, which I feel I have a unique opportunity to do given a small number of mines and a compulsory health scheme to detect cases of mine dust lung disease. I've posted a link here to the first results paper, which is published in the Minerals Journal, for those who would like more information. I expect the second paper on the mine 6 through 8 data to be published soon. Thank you.